Thank you very much, David. So this is the opening workshop of our program, and I would like to welcome you all very much also on behalf of my co-organizers, who are Peter Bartlett, Carola Schönlieb, Arnulf Jensen, and Anders Hansen. So I think we all know how tremendously successful deep learning is these days. I mean, in public life, in sciences, and then in also various mathematical problem settings, but we also know that there is a strong need to improve the theoretical foundation and think about what are the, let's say, the main theoretical avenues, the main theoretical challenges, making progress on those. And so this is also the goal of our Newton program, to advance the research on the theory of deep learning in various different directions, and also, since we all know it's a highly interdisciplinary topic, to also bring together various scientists from different areas, mathematics, computer science, statistics, and so on. And as I said, this is the opening workshop of our program. We will have 4 more workshops. One will be on deep learning and inverse problems, then on deep learning and partial differential equations, then on reliability, safety, explainability of deep learning, and then also on women in deep learning. And so I think we have an exciting program for this workshop. So the lead for this workshop is Peter Bartlett. He was the main organizer of this. And so with this, I would like to now hand over to Peter. Please.
Thanks very much, Gitta. So yes, and thanks to all of the other organizers of this week's workshop. So as well as Gitta, there's Lars Rototto and Francis Park. Yeah, let me add my words of welcome. I'm looking forward to this week, disappointed as everyone that we can't be there in person. I'm told to warn you that we're recording and streaming this, so if you do have questions during the talks and don't want to be recorded, you're welcome to use the chat, but of course we ask everyone to feel free to speak up if they'd like to do that. Okay, so our first speaker today is Emmanuel Abbe, who's at EPFL and Princeton. And we're delighted to have him talking about fundamental limits of gradient-based learning in neural networks. Emmanuel.
Thank you, Peter. So I'm sharing my slides. So yeah, thanks for allowing me to be part of this nice workshop. You can hear me well as well?
Yeah.
Okay. So the talk today is a bit of a storytelling talk where I will kind of try to give an overview of where we are in this line of work of trying to understand what can or cannot be learned when you use gradient-based training on neural networks, when you don't constrain too much what type of neural networks you are using, okay, in this fairly general types of architecture you want to think about. And then I will also talk a bit about, here in the last work, about some recent results that reconnect to more regular type of architectures and initialization. So the questions are the following. To the deep learning framework, we know that what works well is to combine over-parameterized nets with gradient-based training. I would like to understand first how sufficient is the framework, meaning is it specific to certain types of data distributions and architecture like images and convolutional neural nets, or is it something much more general? Could it be universal? In the statistical learning framework, could it be the entire pack class? Is it related to other classes we are aware that we know, like lsquo, or does it have its own class? So these are the first kind of question on the sufficiency of the framework. The second kinds of questions are on the necessity of the framework. Do we need over-parameterization? Do we need SGD for the training specifically? Or if we were smart with our features, could actually kernels compete with what you can get with the deep learning framework? These are the big questions, and one important quantity to define properly for the analysis is what neural networks we are allowing and what type of neural networks. So this is somehow the spectrum from the complexity that we allow. On the very left, you have maybe the simplest type of neural networks, let's say fully connected, IID initialization type of nets, which have been studied quite a lot in the past years. I'll refer to this type of networks, regular networks. I'll define them more formally when we get to that part. And then you can go and climb the complexity, and you can have the convnet, the resnet, and other types of more complex structure like modular net that combine different architectures. And these are, of course, getting more and more complex to describe mathematically and analyze. At the same time, once you go to the extreme of this, where you allow any neural networks that has polynomial size, yeah, I mean, you need at least poly size in order to even store it in the computer. So then again, there's no problem to define this, and this is what I call poly networks. These are just networks with some nonlinearity where you define input output on a DAG, and you just have poly size. So this talk is mainly about this extreme, when you put full freedom on what you can design for your net, and then the last result will be back to the other extreme, regular networks. Okay, so the questions in the free initialization setting, you are given a distribution class. So we know from no free lunch theorem in learning that you need some prior in order to learn, and so you are given a class of potential distributions, and once you have this, you choose your polynet as you want, zero constraint, and then we will ask what distribution classes can you learn. In the regular initialization setting, instead you start with some architecture and some initialization constraints, so some regularity, like we said, IID fully connected. And then you ask what functions can you learn from this type of initialization. So let's start with the first question, the free initialization setting. And the talk will focus on functions that are going, so let me just use this, that are going to be from an input X to an output Y. X, for concreteness, is always going to scale with this input N, which is the dimension of the input. And it's going to be in this talk binary vectors of dimension n, or Boolean vectors. Y will be most of the time also binary classification, but it might be the real line. But in any case, we will always look at the inputs that are binary vectors. So what do we know about these type of functions, the Boolean functions? So we can decompose them, for instance, in one, these are polynomial, right? Because they are on Boolean variables. You can decompose them into the Fourier basis, which are just the monomial. So this chi s f x is simply the product of the xi's. Okay, that's the Fourier wash basis. So you can essentially think of these functions are polynomials that can be expressed like polynomials.
Oi. Olá. Tá tudo.
Okay.
Então, tá ligado da Rita? Ah, não, você não sabe.
Tô.
Ah, desculpa, nada, é só para aprender só a mais
Do
tarde.
you also
Não,
hear
tá a começar agora.
some background noise?
Mas podemos falar? Diz lá.
Hã? Ah, não, é só para saber.
Ah, ok. Tu vens hoje, não vens?
Do you hear the
Okay.
noise as well, or?
Yeah.
Eu estou a dizer horas.
Pá, eu acabo isto
Would it be
bem às
possible for a
6.
host to
Someone
mute?
to be muted, or? Okay, good. All right, so these functions are multivariate polynomials of these xi's, the inputs, xi, x1 up to xn, and you can always express them as monomials. If you look at just the function f of x is x1, then it's a simple function. It's just degree 1 monomial. But if you look at the product x1, blah, 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 up to some x, let's say root n, for example, that's a function that varies much more and is much more hectic. Okay, so what do we know expressibility? We know that if you have a function which is Boolean and computable in polytime, you can express it with a poly-sized network, with a poly network. We also know that from the VC dimension bound, we also know that you can learn this with polynomial sample complexity. So if you stick to ERM, then we already know that polynets are universal. But of course, ERM isn't be hard. So what we'd like to understand is what can you do when you try to use such networks with gradient-based learning. So here is now the class of function, the definition of what we want to study here. So it's SGD NN is the family of distribution. So this is, an input distribution and a class of functions. You could have more generally have a distribution D on X, Y, cross Y. I like to just, for simplicity, work with classes of functions and input distributions. And so these are all sequences as n grows, and you ask what classes of distribution can you learn in the setting where you use some polynomial t and some polygamma, a differentiable loss, which is compatible in polytime, a polynet, with a polytime initialization, such that when you run SGD, with all these parameters being polynomial, then you have that the worst case loss on this class is going to be still vanishing. And I'll define in a second what this SGD is here. The natural counterpart with GD is the same when you use GD instead of SGD. And what are those two is what you expect essentially. So it's the usual recursion of SGD. The gradient is going to be the usual notion of gradient. You do the gradient of the loss, and for SGD, you're going to use a single sample at a time. So it's a new, fresh, independent sample each time. And for GD, you're going to use the entire population for the expectation. And then there is this plus minus tau, this parameter that shows up here in the argument, which is your precision noise. It's basically when you look at your gradients that could be real valued, you will only get them up to some precision tau. So think of tau as something that can be very small, but you don't have infinite precision. Next, we want to compare this to other classes that we are aware of, as we said. So the next natural class is PAC. Sorry for this F that showed up before. You cannot erase in this in Keynote, I think. So this the PAC class is what? These are distribution for which there exists a polytime T, which is the number of samples you get, and a polytime algorithm F at PAC, for which, in fact, you can only, this is just a way to say, when I say you get T independent queries to SAMP, it's just a way to say you get T independent samples from the true distribution, for which you can in fact learn with this property that the worst case loss is vanishing. Okay, so these are just classes of distribution for which there exists some algorithm that uses polynomial sample complexity and that has vanishing loss. And then the last class that we will define is this SQL, which is statistical query learning, which is about the same as PAC, except that there is an important difference. You don't get to see independent samples from the distribution. You cannot query and get just samples. What you can do is you can choose a query function. It's a function you would like to average over, and the oracle only gets you the average, the expectation of this function over the population. And again, with this parameter tau, with the fact that you don't get infinite precision on this expectation, you only get it up to some tau precision. So these are the four main class. This is what we care about, the SGD and the GD, these two. This is two classes that are well studied, the PAC and SQL. One more last notation. It's the, if I omit to put here the argument tau, this precision parameter, it means that I am assuming it's polynomial. So it enters the definition, it's just some polynomial. Okay, so now we're done with all the definitions, we can start thinking about the results. So the first one, which is back to the 99, is due to Kern's when he defined SQL, is that in fact, in this regime when tau is polynomial, SQL is a strict subset of PAC. And what is a separating example? It's those dense parities, which means what? Which means the function x, f, that are of this form. The product x1, blah, 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 up to xk, where k has to be growing. And the input distribution px is uniform on x. Okay, so typically people choose k to be, for example, n/2. So that means your function is a monomial of degree n/2, and you don't know which support it is. So it could be any subset S of size n/2, not specific. That's just one specific example. And this is your class of functions, and this is PAC learnable by doing Gaussian elimination to identify the support, but you cannot learn this by making statistical queries on the data, by getting only averages on the entire data. Okay, so now what we care about is where do these two classes sit in, SGD_NN, and then the other one, the GD_NN. Where do they go? And the choice of colors is not incidental. It happens that this is how they go. So with SGD, you can in fact get the entire PAC class, so you can emulate. So notice that I didn't specify it here, but it's always obvious that this is included into that, because SGD_NN is a special case of PAC, because you're doing something out of samples. And this is a special case of that, because what you do is full gradient descent is going to be a special case of a statistical query algorithm. So now the surprise is that we are saying that this is in fact an equivalence. The two classes are the same. So SGD is as powerful as PAC, it's universal. And GD is not, it's strictly a subset of this class. And it's the reason for this separation is the same kind of reason that there is between SQL and PAC, which is the fact that for this kind of dense parities, you cannot, with gradient descent, extract the details about samples. You are forced to use full gradients, and that doesn't allow you to learn this kind of function. So if you used to, I don't know, well-behaved convex optimization, usually GD is more powerful than SGD because it's better information to average. But when you're in this lens of these functions that are very hectic, like parities, like monomials, then in fact this is playing against you, that you are averaging over the entire population. So here the main result and the main surprise is this one. This one is more expected. In this paper with Colin, we don't actually formally prove this this one here. It follows by the same proof technique for getting this one, but this one is formally proved in the paper I'll mention in a second. Okay, so where are we now? There's two questions that are natural at this point. One is we only consider the extreme of SGD with a single sample at a time, or GD with the full population expectation. What's in between? What if we do mini batch of size B for some B, which is between 1 and infinity? And the second question is that I talked about tau being polynomial in the previous slide, but if you think of tau, so the reason why people typically use polynomial tau is because this is what you need by Chernoff bound to emulate an expectation with a polynomial precision from PAC. But if you think about tau as your precision noise and what you need in a machine to store your gradients, tau could be subpolynomial. It could be lower than polynomial. With a polynomial number of bits to store your gradient, you can go even with a little bit more than log n. You can go with a tau which is omega of log n. You can go with a tau which is smaller than polynomial. So we need to understand these two questions to have a complete picture. So let's define this class, which is the natural counterpart of the previous class. It's B, SGD, and N. We introduce this B parameter here everywhere. And now also here, there's the B, SGD. And we are now, okay, this is just what you expect at each time step of your descent algorithm. Your gradient is average over B fresh samples. And B is 1, you back to what you had in blue, and B infinity, you back to what we had in red, which is full gradients. So where does this sit? And oh, by the way, I should mention that I put a small asterisk on the tau here because before the tau, the noise could be any kind of noise you want to have. Now it's important that the noise it's not important, it's just, it makes our life easier in the paper that this is some kind of rounding noise that you have in precision rounding. Okay, so this is the conjecture. At least that's the conjecture that I put forward. I don't know how clear it is that it is true. Half of it we are pretty sure, I'll say in a second. So the conjecture is that B, SGD, and N, this new class where you play with more generality and B, so again, precision here, and the number of batch per, number of samples per batch, then this would be at least as powerful as PAC. In fact, these are equivalencies. I'm just writing the hard inclusions, the other one are more or less for free. So this will be the entire PAC if this notion of SNR, so what's interesting is this is the ratio that seems to be important. If B times tau, it goes to 0. So B is equal to 1, which is what I had in the SGD in the blue, in the scenario, the first result. And tau polynomial is definitely going to 0. But what this is saying is that there seems to be a threshold phenomena, that if this SNR, which is the product of the batch size per the precision noise, is vanishing, then you get PAC, and if it's blowing up, so you don't get to extract the details of samples in contrast to your precision noise, then the claim is that this is SQL. And what we can prove in this recent paper with this group of co-authors is something which is stronger on the first requirement. We can in fact get even to a constant B times tau, less than 1/12. So in theory, it could be that there's a sharp threshold phenomena that, you know, if you're to a C which is below C0 or to a C which is above C0, you still have this result. I wouldn't go to conjecture that far, but at least here we can go down to constant. And for the other side, for SQL, we need something slightly conjecturally, at least suboptimal, which is that we need B times tau square. So, and then it has to grow faster than log n. So this is slightly suboptimal, I believe, but it still get a fairly tight characterization. And this is something interesting. What this is saying is that this BSGD has this threshold phenomena that you move to either pack or to GD depending on this trade-off on beta. Okay, so perfect. We are about half the time, and this is the current picture. And the conclusion of this current picture, the take-home is that in this framework where you have freedom on the initialization, where you can do any kind of crazy neural nets you want as long as it's poly-size, then essentially SGD is quite powerful. It's SGD is the entire pack, it's universal, and even GD, if you allow yourself with a higher precision, could become pack. Of course, if you start to mess around and put some more randomness on your initialization, this is not clear at all. But in this current setting, it is quite powerful, and this is the take-home. So now what's left? These are the next 2 points to go back to our first questions we had. We wanted to study how necessary the framework is. So we also want to understand if now you do polykernels, which are just kernels with poly many features, could we get the same kind of results? Or do we need to use the deeper neural nets or bigger neural nets? That's the first question about necessity. And the second is if now we don't give as much freedom on the neural nets, but we start to reconnect to what's being done more in practice or even simpler regular nets, then can we still get this kind of results? Or can we compete, or do we have a new class that shows up? Okay, so let's start with the first question, the polykernels. So again, these are just, you have your input here. You choose a feature map with P, which is the number of features. And then you simply assume that, so this is not trained in orange, what you train are those blue edges. It's a linear model on that. And we only assume that those function Phi are computable in polytime. So that's always there in the background. It's polytime computable. And there's poly many of them. Okay, no other restrictions on the type. So normally what I would have done here is define the GD cur class as analogous to what I defined for GD and N. But it turns out there's much more theory. In the case of kernels, we know what gradient descent will produce. So there's no need to say that there exists some loss, there exists some blah, blah, blah. I'll simply write it in terms of representation, which is we would like to understand this class are the class of distribution for which there is a poly set of features, for which in fact, when you choose your feature and the nature picks the function in the class, then when you look at the minimal solution, so this is the projection of your function to these mixtures of these Phi's, the best projection, this overall thing as vanishing error. So this is here taking a shortcut instead of writing it as GD in polytime gets you somewhere. I'm using results that we are already aware of about what GD does on this kind of function. I think I'm thinking of the L2 loss here, but I don't think it's required here, but that's how I think about it. And therefore, so this is just essentially the class that we care about. GD kernel is whenever this big number here, which is only optimizing over the choice of the feature, is going to be still vanishing. That's the vanishing loss property. So where do you think this sits? So this is the picture we had up to now. SGDNN was universal. GDNN was saturating to SQL, statistical query. This one navigates in between. And now we would like to understand where does GD on kernel go? Could be a subset of SQL, could be bigger. And so the result is that it's going to be strictly smaller. It's going to sit here below SQL with a separation. And here is the formal theorem. So actually, here I state two results at the same time. So if you take this class of sparse bias parities, which I'll define in a second, then there exists a differentiable model and also a poly-sized net, such that GD with polynomial parameters learns with zero loss, so exactly zero loss. But any polykernel must have a trivial loss, like tending to 1. So 1 is the worst case. It's normalized to be the worst loss. So what's the there's two refs simply because in this first paper we use a differentiable model that's not a neural net. With the second paper, you get it with a poly-sized net. Okay, so what is the sparse bias parities and why can't you not learn these with kernels? So these are the functions. They are again like we had before. They are monomials, so it's just x1 times theta times xn, and any permutations of these variables. Sorry, xk, and the k here now it's going to be log n exactly. And the xi's are no longer IID Bernoulli half, which is a uniform measure, but they are IID Bernoulli B, where B is some bias, which is constant. B is some number between 0 and 1, or 0 and half. Okay, so for instance, B could be a quarter, and that is a sparse bias parties. Okay, so what's happening with this type of function? So if you define Fs, the product of the xi that are in S, if this is your notation, then the difference between dense and sparse parities is that when you look at the inner product between two sparse parities, then this is going to be the expectation of the product of the xi that are in the symmetric difference, because xi square when you are in the intersection. And because the expectation is going to be B, so it's going to be B times the size of the different sets. So if B is like a quarter, so this is the bias. So let's have to reparameterize. So this is going to be the expectation. So it's not exactly B. It's something like B times 1 minus B or something like that, but it's a constant. So this, if this is logarithmic, because of the choice here, typically it's logarithmic, and this is a constant, then this can be polynomial now. It's going to be n minus some other constant. Whereas in the dense parities, these inner products, when you do dense parities, so let's put tilde for sparse, this is exactly 0 unless s is equal to t. So now there is some correlation between those sparse parities and the fact that it is biased. But it turns out that those correlations are still not enough for kernels of polysize to catch the function. And the lower bound is actually the most interesting part here, because there is some polynomial correlation between such functions. You are allowed to use polymany features. So it's not obvious by just trivial bounds that you could not accumulate altogether a good loss by being smart in choosing your features. You have to do a fair amount of Fourier analysis to prove that you cannot actually get a vanishing loss. But this is the intuition, is that you will actually not be able to do it. It's just not enough to do it with kernels. But if you have a deeper net, then you can do smarter things and start, trying to detect first the support of the parity and then try to learn the functions on the support. So you need to do this kind of two-step approach that you cannot do with a kernel. Okay, so I have to mention that there's been lots of reference on studying this separation between kernels and neural nets. We did in the paper a fair amount of work to include an exhaustive, or we tried to be exhaustive literature review. I think the new component of the separation result that I talked about is that it's the first separation that gets you that the kernels gets nothing, gets a trivial loss, while the neural nets can get you perfect zero loss. So it's this strong separation phenomena that is new. Okay, so that's the answer for kernels. They can't quite compete even with polysize. They are a strict subset of even what GD can get on neural nets. And now the last questions in the last 5 minutes is let's go back to, I didn't tell you much about what the university result uses. So this, to get back with SGD, the neural nets, what it tries to do is to emulate whatever pack algorithm you have at hand, which means that we are building a neural net such that when you use stochastic gradient descent as your way to update the neural net, you can essentially, by carefully designing the net architecture and initialization, you can essentially emulate any algorithm. And so we have a computation component, a memory component, some control vertices that allow you from back propagations to change the memory as you want. And this is clearly something which is there to tell you you can learn pack when you have freedom, but it's not exactly, or it doesn't seem to be at all like deep learning works. Okay, so it's more there to see if you don't put constraints on the neural nets, then it is everything, which in a sense, okay, it's good to know, but it's unlikely to explain how deep learning in this more black box fashion seems to work. So let's try to go back to regular nets, okay? So here is what I will define. We have this new class now, SGD, so you can define it for SGD or just GD. That's what I put the parentheses on S. I add the reg requirements. And this means that, again, everything in polytime with poly parameters, except that now, before we simply had the exist W0 initialization that was polytime. Now it's got to be a polysize and regular architecture, and the initialization has to be also regular. So what's this? What's the regularity here? It means the following. So I'll define it on the picture. You have a set of input which are the the usual variables, the monomials of degree 1. You predefine a set of layers with a bunch of neurons per layers. Between any two consecutive layers, you put edges with an Erdős-Rényi bipartite graph, which simply means you put any edge independently with some fixed probability p, and it's going to be the same p all over the nets. And then you also allow for edges that go from the input to the middle, and these are also placed independently with the same probability q. And then you allow edges from the middle to the output, and these are again there independently with the same probability r. Okay, so with this kind of constraints, oh, and I forgot. And then you put the values of the weights at initialization also in an IID fashion with some distribution of your choice, but it's got to be IID. So if you do that, then every layer is going to be permutation invariant in the sense that if you apply a permutation of any neurons in the layer, then the W0 is going to be the same in distribution as the W pi 0. So there's a lot of homogeneity in this net. So as far as I'm concerned, I cannot think of any way to redo what I described, what I told you before in the talk, all these emulation that we have when you have such strong homogeneity constraints. And you cannot do the kind of emulation stuff that are described here. Okay, so what can we say then about this class, this new class, once you have this stronger regularity? So first of all, notice that we know that GD will not learn because of the SQ bound. It can only learn finite degree monomials. Okay, so you cannot hope to get much more. We have some other results that say that in this setting, it's likely that SGD saturates at the same level. But here, what's important is what will be your guess? Do you think that when you have the regularity, you can still get SQL, which is what GD can get when you don't put any constraint on your nets? Do you think that maybe you can only do finite degree polynomials and you cannot climb to high degree terms? Or is it something else? So again, this is my conjecture. I don't know. I was talking to Henrik. So Henrik Boix is the main protagonist on this work. I don't know how much we agree on this conjecture. So let me take the responsibility for it if it's wrong. So here is the picture that I claim, which is that this set of GD, NN, reg sits between what you can do with kernels. So it's strictly more powerful than kernels, but it's also less powerful than what you can do with full neural nets that are free. And a bit more precision, I'll tell you in a second. Here is a candidate for a separating example. These are the truncated staircases. I'll define them next slide. Next slide is my last slide. And then here, the reason why you're still separated from kernels is again by this sparse bias parity, for instance. More importantly, we might have a shot at characterizing what you can actually learn with this reg. And this is our HBF. So let me define these guys now. So this is a staircase function. It's a Boolean function that can be high degree. You can even go up to the high degree monomial, the one that if you didn't have, if I remove all of this block and I just have this guy here, then this is the guy that you cannot even learn with SGD or sorry, with GD, because it's not SQ learnable. It's the, the most hectic function that is the hardest to learn. But you can have this term in your function as long as you have a staircase. What's a staircase? Is the fact that you must have the other Fourier coefficients that are nested and that allow you to climb there. So you must have the first one or one of them, and then you must have the degree 2, the degree 3, etc. And these are nested in each other. So this contains the previous guy, this contains the previous guy, etc. Okay, so that's the pretty intuitive name of staircase. More generally, and I'll define it informally, we define this paper the HBF, the hierarchical Boolean functions, which means that any high degree Fourier coefficients is composable by lower order coefficients that show up in the function. And these, if they are not constant, they must be composable by lower order degree coefficients that are in the function, etc., until you hit the constant degree. And what we can prove in this paper is that if you use gradient-based learning, I don't say gradient descent here because we can do something which is as plain as gradient descent. We do some sort of coordinate descent. And it's not, we'd like to do gradient descent, but it's a bit more specific at the moment. It's still gradient-based learning though. So you can use gradient-based learning on this type of regular neural nets. And what we use is some sort of, what I described to you in the previous slide. We just choose the P's to be in the sparse regime, makes our life easier. And then you can learn in polytime this kind of staircase function, this idea that you can actually get high degree coefficients as long as they are climbable by low degree ones. Okay, so now in the last minute or 30 seconds, I tell you just quickly why, what are these two objects here? Maybe that's the most interesting. The truncated staircase are simply this, is you go back to the staircase, but you truncate it, meaning you don't take the first term. So you start at the term x1 dot x with a coefficient k, which is growing, for example, log n. So if you have that, then your net, that's the conjecture, and I'll tell you why I believe we can eventually establish this. Then you cannot, when you start from your x1, xn inputs, which are degree 1 monomial, then there's nothing in the laws that gives you the incentive to come up with those guys that you don't have. And therefore, you never get to climb to this guy, which is a diverging degree. And so you don't get to learn these kind of functions. That's the conjecture. And what are those sparse bias parties, and why can you learn them with HBF? And I will just write this simple equation. If you look at the product x1, x2, when these guys are sparse, biased, when the expectation is a B instead of a 0, then this is nothing but this. I center each term here. And then I erase what I added. So I have to add a B x1 minus B. I have to add also a B x2 minus B. And then I have to compensate for the B square. And so this is what? This is simply x1, x2 tilde plus some coefficient x1 tilde plus B some x2 tilde, where I'm working now with the centered monomials, which is in fact the proper Fourier basis when you work in the bias setting. So in other words, the sparse bias parties are staircase function. This is what this is saying. And this is why, in fact, you can learn them, we believe, with those regular initialization, and that we can prove for the most part, except we still need some hacks. So that's the conjecture, or that's the picture that we have or almost have at the moment. And I'll stop here. Thank you.
Thanks. Thanks very much, Daniel. So we actually have one question in the chat from Sebastian. What is the depth that you need in ABBN21? Can you obtain this result with layer-wise training, or is it important that the whole network learns simultaneously?
Okay, thanks, Seb, for the question. It's actually, so first question, the depth, it's polynomial. It's n to some huge constant. It's, I forgot what it is, but also the width is about, I think we take it n to the 100 or something like that. So it's for the proof, you know, we didn't try to pin it down to the right polynomial, but it's going to be polynomial. And it's actually the descent algorithm we use is already, it's okay, we have two of them. We have one which is layer wise because it makes our life easier. And we have one which is this coordinate descent version that picks a neuron at random and train that neuron, and then picks a new neuron at random and train all the edges entering that neuron. So it's actually not it's not doing the whole thing at once already, but more by constraint than anything else at the moment. We also have a fair amount of simulations that I did not include that show that you can learn these staircase functions and these HBF with classical resnets. So these last papers that I mentioned, this one about the regular class and this one here, they are supposed to be posted today or tomorrow. It's essentially, that was the deadline, was today. So they should be on archive next days.
Great. Thanks very much, Emmanuel. We're running a few minutes behind, so yeah, let's thank Emmanuel again.
Thank
and
you.
move on.